All right, so today we're talking about automated market makers and more specifically, constant product market makers, which is what Uniswap is. Automated market makers allow people to trade through smart contracts that are connected to liquidity pools. Centralized exchanges usually implement order books and trade off chain. So there needs to be a coincidence of once, and you don't fully own the assets that you trade, which is only cool to people like Sam Bankman-Fried. The key rule of constant product market makers is that the balances X and Y of each token must multiply to a constant K. This is what that looks like on a graph. So if someone wants to take one token out of the pool, they have to put in whatever amount of the other so that they stay somewhere on this curve.
So like if this is like ETH USDC, like
Mhm.
you have 100 ETH and 100 USDC,
Mm-hmm.
then it would just be like 100 times 100 equals what, 10,000?
Yep.
And 10,000 would be K. So then do you have to like set K when you
Yeah, that
deploy
was my
this thing?
question.
I don't think so, right?
So like in the most basic form, K is just determined by how how deep the liquidity pool is.
Oh, right. So K actually changes. So it's like sort of a
Yeah.
constant, but
Yeah, I'm not
it's a constant given a certain amount of liquidity, right?
right, right.
Yeah. Okay.
K K will always, I mean, if we're talking about the price of an asset, K will always tend to be what the price is on the centralized exchanges because if it's lower, people will buy the
Okay.
asset to arbitrage it and stuff like that.
Right. Yeah, arbitrage plays a big role in these. Um, classic supply and demand still in effect. The less of one token there is, the more expensive it gets. As Buddy said, arbitrage plays a big role in keeping this like wherever we are in the curve to match the state of the current market. There are some newer projects like Dodo Exchange that use market price oracles to proactively adjust some parameters related to K. I'm not exactly sure how that works, but today we're just taking a look at constant product equations. So let's use our imaginary liquidity pool with token 1 and token 2. Right before a trade happens, we have X amount of token 1, Y amount of token 2. But let's say you want to acquire some token 2. So if you want to take token 2 out of the pool, you have to put some amount of token 1 into the pool so that the respective balance of each still multiplies to K. And that gives us this new equation about a pool after the trade. And this will tell us a lot of important things about the trade. So if we do some algebra here, we can solve this for dx. So first we're going to multiply these two things. First times first, first times second, second times first, second times second. And we get k equals all of this.
So this would be like, I guess just breaking it down into actual examples. Like if you have if X is 100 and Y is 100, like it's said before. So like you would know that before the trade. So there's 100 of each in each pool. So K is 10,000,
Yep.
right? Then you would say like, I want to put in some amount of X. You would say like, I'm going to send in 10 ETH. How many USDC am I going to get out? Now you would be solving for DY, and that would be in this.
Yeah.
Yeah.
Yep.
Does that make sense, guys?
Mm-hmm.
Okay. And that would be like how you would write it in Solidity or whatever.
And the same argument applies. You could say, I have this much. How much am I going to get out? Or I want to get out this much. How much do I have to put in?
Yep. Cool.
So if we keep going with some of the algebra here, from this second equation, we know that xy has to equal k. So we can trade xy for k here. And now k equals k plus all of this. And if we subtract k from both sides, all of this stuff has to add up to 0. And this, we can play around with this a little bit and actually solve for dy or dx, which is how much you have to put in or how much you have to take out. So if we want to solve for dx here, it doesn't really matter. Like we said earlier, you could solve for dy. But let's solve for dx. Move this x dy over, factor out a dx, and divide by this quantity y minus dy. This is how you determine if you take out dy amount, you're going to get dx, and vice versa. This is what you end up getting for dy.
So yeah, you don't even need a k.
Mm-hmm.
Yeah.
Yeah, for determining the balances. Mm-hmm. So let's talk a little bit about the price. The price is determined by the ratio of the token balances. The spot price for a token is given by the amount of the other token divided by the total amount of the token that you want the price for. And that is actually the tangent line to the graph at whatever state the pool is in. It's like if this is our before, this tangent line, this slope is the price you pay. But that spot price is like the price to trade an infinitely small amount. You don't actually pay that. You have to pay a little bit more. The effective price is what you actually pay. And that is the slope between the state of the pool before the trade and the state of the pool after the trade.
That would be the slope at that midpoint of that curve, right? Yeah.
Through the 2 points. Do you mean midpoint like right here?
Yeah, right. Looks to be about the same, right?
That's only because this point, like, because this point started like perfectly here.
Oh, okay. Yeah.
We could have a trade like here and end up here.
Right.
Oh, I see what you're saying.
Why is that the spot price? Why is it an infinitely small amount versus why is that the effective price?
So the spot price is coming from the total pool balances. But you don't get to trade with that price. The amount you pay has to factor in how much you're putting in and how much you're taking out. So we can't just use the total balances. Because Nick, what you were saying earlier, yeah, this
Would
is
just
midpoint.
yeah.
Mhm.
But spot price and effective price are like usually similar unless you're trading like a lot of coins, right?
Right, exactly.
Okay.
Yeah, if you make like a massive trade, you're gonna get a way worse deal than the spot price. But if you trade like a super tiny amount, you're gonna pay really close to the spot price.
Or if there's a ton of liquidity, because it's all relative, right?
Right.
Yeah.
Mhm.
So
And because of this bowl shape, you always pay more, kind of what we've been talking about. You always pay more than the spot price. The difference in spot price and effective price is known as the price impact, also slippage. You have to allow a certain amount of wiggle room for your transaction based on transactions that happen right before you. And that's actually a vulnerability of these markets. There's something called a sandwich attack, where if you set too high of a slippage, you can kind of get juiced by a bot front running your trade to give you a worse price, and then trading that back to the pool where it would be if you had proper slippage. How about we run through an example using this? So let's say we have a pool with 200 Ether, 800,000 USDC. Well, then the spot price for Ether in terms of USDC is the total divided by the total. So you get 4,000 USDC per ETH. But suppose you have 200,000 USDC and you want Ether. Well, we can figure out how much Ether we're going to get from the equation we rearranged earlier. So if we plug in what we know that there's 200 ETH in the pool right now. We're putting in 200,000 USDC. There was 800,000 USDC. We're putting in 200,000 more. We're going to get 40 Ether out of the pool. So 40 Ether comes out of the pool, 200,000 goes in. The effective price you paid then is actually 5,000 USDC per ETH. And that's such a big difference because the trade was so large relative to the pool's liquidity. And let's say like the market price was like 4,500. Arbitragers would immediately come in and eat up the cheap USDC for that overpriced Ether. Another important idea, when there's no fees, if this trade was split into two smaller trades, like each 100,000, you would still get the same amount of Ether.
Well, what you would hope would be like, if you split it up, you would probably want to like split it up into one trade and then like hope arbitragers push the price back down and then go in and do it again. Right?
Yeah.
Is liquidity just determined by the amount of the trade compared to the amount that's already in the pool? That's like there's no constant that directly that dictates what the liquidity is. It's just the
Liquidity is how much is X and Y. So yeah.
What were you saying?
X plus Y
Times. Mm-hmm. Yeah, Uniswap calls K L squared. To be honest, I'm not exactly sure how that too much about that relationship. I'll have to look more into that.
And like the K or the L squared, are those like terms used other places in math? Like, does that mean anything? Like, you know, X and Y are just variable names. Did Uniswap like make up the letter K? Is that the reason they use it?
It's a nice constant. Yeah.
Okay.
Yeah. So this has all been assuming there are no fees. But in reality, there is a fee for every transaction, so that there's incentive to put up liquidity. This is the formula that Uniswap V2 uses. So they take a 0.3% fee. So they pretty much say, we're only counting 99.7% of what you're putting in, and you have access to 99.7% of the token you want to acquire. And once we start adding in the fees, the splitting up your trade into multiple smaller trade scenario gets much worse. That's
You-
pretty much it for
Oh.
today. Does anyone have any questions?
You can set the fee when you deploy a pool, right? On Uniswap.
In Uniswap,
Uniswap V2.
I'm actually not sure. I'll have to look
Oh,
into
okay,
that.
no problem.
Anything else?
No, any questions, guys? This was awesome. I actually feel like I understand it way better now.
Yes.
Yeah. So thank you very much, Dan.
All right, good. Glad I could help.
Thanks.
Thanks,
Yeah.
Dan.